I want to just take a moment to say a big thank you to Rockwool North America. Rockwool has been a founding sponsor since the very early days of Passive House Accelerator. So back in 2019, they've supported our development and growth for all of these years. And we are just delighted to be in partnership with Rockwool. And you are in store for a treat today. You know, one of the major benefits of Passive House is the serene environments that they can provide, nice, quiet, serene environments. And so we'll learn about one of the key materials that makes that possible today. So with that, I want to introduce today's host of the Component Spotlight and also the Q&A concierge, Sarah Nuama. Sarah, thanks so much for joining us today to be part of this. Sarah is the Clean Energy Project Manager with the Portland Clean Energy Community Benefits Fund. She's also the Passive House Northwest Board President, and she is also a very active co-host of many Passive House Accelerator live events. So you've probably seen Sarah, and she's gonna be your host today. So Sarah, please take it away.
Hello. Thank you so much, Zach. And hi, everybody. It is really great to see some of your faces today. And before you dive in, just a quick note on participation if you're new to the crew. So we are very curious to know where you're joining from in the chat. If you would, drop where you're saying hello from. It's a pretty rare sunny day in Portland for this time of year, and that's where I'm calling in from. Um, Also, feel free to drop some questions in the chat as you think about them during this presentation. We're gonna go ahead and save some time at the end for a live discussion and question and answer time. And we will, we encourage you to make this as interactive as you want it to be. So if you have some questions that pop in, we're gonna generate a little queue and then we'll kind of go from there. And I will invite you to unmute and ask your question. And if not, I will ask it for you. These sessions are always a little stronger when the community engages, so we just love to have that discussion-based Q&A time with you all. And kind of echoing Zach, a huge thank you to Rockwool for joining us and also for their, long-going support for Passive House Accelerator. We really much appreciate that very much. And without taking too much more time, I'm so pleased to welcome our guests today. We got some Rockwool folks. We have Antoine Habelion, the technical director, and we have Robert Blount, the architectural manager for North America. So thank you, you two. We're very excited to have you here, and I will hand it off to you.
Good afternoon, everybody. Good morning if you're on the West Coast or somewhere further east than where I'm sitting north of Boston. Thank you, Zach, for shouting out Nessie. You saved me a step. Thank you for joining us here today for our presentation, Sound Off Designing for Optimal Acoustic Performance. You can forward the slide, Antoine. As Sarah mentioned, my name is Robert Blunt. I'm the architectural manager for New England. I'm also co-chair of the Building Closure Council here in Boston, where we try to help everybody keep abreast of all things enclosure, especially as we are some of the most progressive code in the country, including Passive House in all of our multifamilies in the Boston metro area, as well as some pretty stout requirements in terms of air tightness and thermal barriers and thermal backstop. But more importantly, I am joined by my colleague Antoine Habelion, who is our technical director and one of my favorite folks to work with here at Rockwool, because he is the guy that we go to when we have really difficult questions from a technical perspective. Slide, please. Just a little bit about who we are, where we are, before we get into the meat of the presentation. We've been in North America since 1989 with a start in Milton, Ontario, where we have our first production line. We also make our sister company's products there. Grodan, who does hydroponic growing medium. We have 3 other manufacturing facilities, one in Grand Forks, BC, which does a lot of material for OEM. So for us, that means insulated metal panels, stuff like Kingspan, Centria, Trimo, soon to be, Ransom, West Virginia, and Bahia, Mississippi, who also makes some of the product for our other sister company, who is Rockphone, based in Chicago, Illinois. They are the grid ceilings and panels side of our business. Slide. If you're not familiar with who we are, what we do, I think the one thing to understand is kind of some of the intrinsic nature of our products. So we make stone wool insulation as as our core business. The benefits there, of course, are that it's made of stone, so it is extremely fire safe, very durable. Stone lasts forever. Very moisture resistant. The binder that we use to put all of our board and bat products together is extremely hydrophobic. So from a building science perspective, that means that we are served well in everything moisture and moisture management on the thermal barrier side. Also very breathable, right? Permeability means quicker drying potential in our walls. And apropos to this presentation, that fibrous matrix gives us a really great profile in sound mitigation. And also things to think about as we're picking all the materials that we design. Circularity, we are starting to take material back in Europe and put it back into our manufacturing stream where we've been making and having material installed for the longest. Here, slide please. We work in conjunction with a number of partners, not just the Passive House Accelerator. Lots of folks in the Passive House space, lots of folks in the sustainability space. The one that somehow didn't make this page is, of course, NESE, the Northeast Sustainable Energy Association. So for those of you, I see a couple in the chat that are here in the Northeast, we'd love to see you on Monday, Tuesday in Boston. Slide. Just a quick profile on where you might see our materials. Of course, we're an acoustic mitigator as well as thermal insulation. So everything in the wall plate and the floor plate. Fire safing at our edge of slabs, fire stopping in penetrations throughout our building and at head of walls. We have a very high density roof board material. And as I mentioned, our core solutions product lines are primarily insulated metal panels and to a lesser degree, folks that make engineered sound panels. And last one, Antoine. I want to mention that we have a series of masterclasses, if you will, that we do in a digital format online. And we have one coming up next week, a week from tomorrow on the 26th. Take a minute to scan this QR code. This is the second in a series where our Antoine's colleague, Ali Al-Janabi from our building science department, along with Dr. John Straub from RDH Building Science, will be presenting content on retrofitting existing buildings. A lot of really great information on retrofitting mass masonry from the inside and managing all the building science aspects of that process. Definitely, it's worth the hour, and of course, you get an AIA CEU. And without further ado, I'm going to let Antoine take over, and hopefully, in about 40 minutes here, we can get conversational and talk a little bit about what you see here. And we'd love to answer some questions about how we can help you with the projects that you're working on.
Thank you, Rob, and good afternoon, everybody. I'm not sure if I should say good afternoon, good morning, good evening. I saw in the chat there's really people from all over the place and including some very far countries. So anyway, happy to be here. And so just as maybe a little disclaimer before going through this presentation, I would like to emphasize the fact that I am a civil engineer by training and not an acoustician. And so, while I have developed quite a good amount of experience in acoustic in my almost 15 years at Rockwool, I think it's important to note as a piece of information before going through this. So now let's talk about how to make our buildings more acoustically efficient. And in fact, this is a very important subject, a subject that's very dear to my heart. And mainly because for most buildings, I want to say that it's a topic that we tend to neglect. Uh, Acoustic is either a topic that's incredibly important because it's a, it's a concert hall or an area, a space that's specifically used for sound. But whenever that's not the case, we really tend to just kind of ignore it or treat it in a very simplified manner. And so as a result, it's usually not so good. We'll come back on that. But so from an acoustic standpoint, the sound that we want to block, which we perceive as noise, are essentially the same thing. Sound and noise are the exact same thing. What the reason why we use a different word is essentially because noise is a sound that we don't like to hear. And what's interesting to note about that is that what is sound to someone and something that is good to hear may be actually noise to someone else. The most probably simple example would be someone watching TV in one room and someone trying to sleep in the adjacent room, where there is a shared wall between the two rooms and the noise from the TV is just traveling through the other room. And so it's very important in our design to account for these things and if we really truly want to make our building more comfortable and better for health, it is important to account for this complicated concept of noise and sound in a better manner. And noise can have a very significant impact on our life. It is estimated today, so it's lucky that there was just a very recent update from the World Health Organization. You can see from March 2026, so it couldn't be fresher statistics, but it's estimated that about 1.5 billion people currently live with some degree of hearing loss. That represents nearly 20% of the global population. And that's important. I will come back about this in a minute. But hearing loss could mean things such as difficulty to communicate, isolation, etc. Right? If you are if you're having a conversation in a loud environment and you cannot hear the person that you're having a conversation with, naturally it's going to isolate you. And so it's very important to account for this kind of maybe more simple, more common, more basic needs. The comfort is not just about people with very severe disabilities, but it's also for people, in fact, like me, as a non-native English speaker. I can easily testify to the fact that when I'm having a dinner after our sales meeting at Rockwool and we're in a very loud restaurant, it is difficult to have a conversation because I simply struggle a lot more to understand the people I'm trying to have a conversation with. It's also estimated that there's about 430 million which actually have disabling hearing loss. So this will be significant impairment. So it's a very, very significant number. And that number is expected to rise by 2050 if the trend continue. And one of the things that's making these numbers worse one year after the other is that essentially we live in a very loud world. And it's very difficult nowadays to escape sound. So, if you live in Toronto or in New York City or in Chicago or really any, dense big city, you probably can definitely also testify to the fact that these cities are very loud and they tend to even stay loud at night. And so we have this constant exposure to noise, which eventually can lead to hearing loss. And so bad acoustic, being subjected to noise for significant duration can have very significant health effects. So it obviously starts with minor things such as hearing some minor hearing loss and potentially eventually tinnitus. So the constant noise that you may hear in your ears after being exposed to a loud noise, for instance, after a concert or something like this. But the tinnitus can actually become permanent, and it's obviously a major discomfort. It can also, as I was saying earlier, reduce the ability to communicate, to comprehend people, and could potentially limit social interaction. It can also lower productivity in an office space. It can increase stress. It can increase the risk of cardiovascular effects, and eventually can actually, lead to very serious cardiovascular diseases such as strokes. So the effect of being exposed to noise, permanently are very, very important, and we really should not neglect them. What's interesting with acoustic, as I was saying earlier, as a short of introduction, is it's typically an area that's not so well considered. You know, we tend to talk a lot about thermal comfort and thermal performance, energy efficiency, air tightness, all these kind of things. But acoustic tends to always fall behind. And, you know, in design, and in fact, I would be interested to hear from the audience here how often you actually, you know, have more than a just very basic superficial conversation about acoustic. But I will guess that for most of us, it's probably not that often. And so some years ago, there were a study conducted by the Center for the Built Environment, where they essentially surveyed 90,000 people from approximately 900 buildings, so a pretty significant sample of people. And they basically asked how people were satisfied around all kind of things. So there was, for instance, the amount of light, the air quality, the cleaning, the visual comfort, the personal workspace, the furnishing, all kind of the temperature, all kind of different things. And you know, temperature, I think you wouldn't be surprised to see that quite a good amount of people were not satisfied, because we tend to, you know, in a shared office building, for instance, we tend to fight a lot about the temperature and the thermostat, and that's because, you know, people have different metabolism, they dress differently, etc. But the area that came up at the worst was the sound privacy, and noise level was also very close. So acoustic essentially was by the most considered, you know, a major problem. And I think, again, it's not surprising, right? Because in most typical buildings, acoustic tends to fall really far behind and is usually kind of overlooked. So now let's go to a little bit to the fundamentals, and for the sake of this presentation, I won't go too much in depth, but I think it's important for all of us to understand some very basic principle. So the first thing is, what is sound? So sound is essentially a pressure wave created by a vibrating object. So for instance, me talking right now, you know, inside my throat, I actually don't remember what's called in English, but, you know, I'm sure you guys all know there is something that creates a vibration in the air, and the sound is traveling through the air by vibrating the particles in the air. And obviously this can happen through the air, a gas, liquid, solids, etc. But it's basically a vibrational motion. And as this sound wave is traveling through space, it loses energy, which is why the further you are, the less loud the sound is. And sound is typically measured with sound pressure levels, and it could be essentially, you know, pressure in Pascal, for instance. The thing with sound is that the level of pressure that we will consider from the softest sound we can hear to the loudest sound we can hear is so widespread that it's very inconvenient to speak with pressures. And this is why in acoustic, we always, you know, use decibels. So decibels is not an actual unit. It's not a quantity. Decibel is a ratio. It's essentially a ratio when it comes to acoustic of the sound pressure we're talking about. So let's say, for instance, me talking right now. It's a ratio of the sound, the pressure of me talking right now with the threshold of human hearing. And so essentially what we're doing with decibel is we're comparing the sound pressure with that softest sound that we can possibly hear. And that creates a much more manageable scale where typical sound will vary between maybe, let's say, 30 decibels or 40 decibels if you're having a quiet conversation. You know, actually in this chart, we're showing 60 decibel for like maybe a meeting room or something like this. And you will go, for instance, at 120 decibels for, you know, an emergency ambulance going in the street with a siren on or something like this. And all the way to maybe 140, 50 for a gunshot, for instance. And so it is a much more manageable scale. Now, what's interesting is that because it's a ratio, and it's in fact you know, to go from the ratio, to go from the pressure to the decibel amount, we use a logarithmic scale. So it's a bit of a complicated scale. And what it means is that the difference of 3 decibels, for instance, is very significant if you think of a logarithmic. So the decibel is a little complicated it's a bit of a complicated measure it's easy to talk about decibel. It's a bit more complicated to comprehend, I think is the point I want to make. But so the amplitude of the sound, which is what we measure in decibel, is what we will refer to in simple words as the loudness of the sound. Another very important property of the sound is the frequency. And I think for the frequency, I think it's much easier to understand, and most of us are probably having a much easier time to understand what it actually means. But so this is a frequency of the sound wave, and it essentially referred to as the pitch. So low frequency noise would be, you know, a low sound such as a rumbling from, you know, the train going on the track nearby, and a high pitch noise or noise with high frequency could be, for instance, an infant, you know, talking or crying. And so a typical sound is going to typically be composed of multiple frequencies. So now that we have these very basic parameters, very basic properties, I hope I was able to, you know, simplify that enough and that it was clear enough. But now we have these basic properties. Let's talk to sound isolation in building. So in order to provide a good acoustic comfort in a building, there is multiple things that we want to do. And that we want to address. The first one, the most obvious one, is to address airborne sound. So airborne sound would, for instance, be me speaking. By speaking, I said by the particle of the air in vibrational motion, and that's transmitting through the air. Eventually, will reach a wall, and eventually might start vibrating the material of the wall, the solids composing that wall, and transfer to the next room where the wall will transmit that vibrational motion to the air again, and it will get to the person in the adjacent room. So the first thing we want to address is, again, airborne sound. Then we have what's called structural borne sound. So that could be someone, so if you look at the sketch on the right side of the slide, you can see someone walking on the upper floor, and you can imagine that every time this person steps on the floor, it creates an impact on the floor, and that creates what we call a structural borne sound. The sound starts from the structure being hit. And then we have flanking sound. This one is, even for people who are interested in acoustic, is typically the one that then gets kind of forgotten. And so the flanking sound are sound that will travel through indirect pathways that are less obvious. So let's imagine, for instance, an office building where we'll have, you know, partitions separating spaces. And it's very common in commercial buildings to not build the partition all the way to the ceiling or the roof deck, and to essentially stop that partition at the plenum level. Now imagine you have light fixtures, ventilation grid, and maybe a conditioned plenum. Well, the sound, the airborne sound within the room, has the ability to travel from one room to the next just by going through the vents, through the plenum, and back into the room. So that's what we will typically refer to a flanking sound. It's not a sound that's transmitting directly, as we will, you know, simply imagine, from one person directly to the next, or from one room to the next by going through the wall. But it's these sounds that are taking different pathways, connections between floor and walls, you know, gaps that we may have forgotten, or poor air leakage. And obviously here we have a community very interested in passive house. So you know the importance of air leakage from an energy standpoint. Obviously from a sound standpoint, it's also very important. I always like to provide the example of, you know, you're in a room and you don't hear the street noises. You open the window. Obviously, if it's winter time, you may have a lot of heat loss through that window, but you're also certainly going to hear the noise in the street much better, because you essentially create a hole in that air barrier. So air tightness in acoustic is also very essential, and especially to deal with flanking sounds. So there's many different basic properties that it's important to have in mind when thinking of acoustic. The first one is the noise reduction coefficient, typically referred to as NRC. It's a standardized rating. If you're like me, you're into ASTM standards and the nerdiness of these kind of things. It's ASTM C423 that describes how to measure this. On the right side of the slide, the photo that you see is actually a room in which you will be measuring the noise reduction coefficient of a material. So this standardized rating is used to assess the performance of a material alone. And mainly its ability to absorb sound, because sound absorption will be helpful to decrease reverberation, loudness, increase privacy, intelligibility, and comfort. So imagine you're in a restaurant and it's a super fancy design, it looks super modern, but all surfaces are, you know, tiles and concrete, polished concrete. It may look cool, but the sound, as you can imagine, the sound quality within the space will be very poor, because all this hard surface will eventually reverberate the sound. And so you will be using, in this case, acoustic materials which are good at absorption to reduce this reverberation. So the NRC is the first metric that you can use. So it's very useful, for instance, if you do like commercial work, it will be an interesting parameter, for instance, when you're specifying ceiling tiles, because the ceiling tile, they will be used mainly for the acoustic within the space, not between spaces, but within the space, the acoustic quality of the room itself. Then what we need to focus more on is not so much the sound quality within the space, because I think ultimately this one we tend to do a better job at, even though I think my comment about restaurant is a fair one, where a lot of bars and restaurants tend to neglect that, to have a cooler design, if I may say so, and end up with bad sound quality. But I think for the most part, like if we think about passive house, single family home, typically the sound quality within the home itself, like within rooms, is going to be quite good, because we have, furnitures and rugs and things on the wall, cabinets and paintings and so on. So the sound quality within spaces tends to be good. Where we are not so good is really to block sound from spaces to spaces. And so this is what I want to basically put into the concept of effectiveness of a structure. So in order to do a good job at creating acoustic within different spaces and to block sound from one space to another, there's various things that we need to do. But sound blockage, which is this ability of blocking sound from one space to the next, is directly dependent on the weight of the assembly. So you can easily, I think, imagine how a concrete wall, for instance, if you live in a condo where typically the units are going to be separated by concrete walls, the ability to block the sound from one space to another, airborne sound, not structural sound, not the ones where it's impact, but airborne sound with heavy concrete walls, typically good, as opposed to a very basic wood frame wall with gypsum on both sides between a bedroom and a living room with no insulation within the stud cavity. The heavy concrete wall, I think it's fairly easy to imagine, is much better at blocking the sound. And that's because, remember, sound is essentially energy. It's a vibration of the particles. The heavier the material, the more energy it requires to move these particles. And so a concrete wall requires more energy to start vibrating than just a very lightweight basic partition wall. So another thing that's important is to think about sound absorption. And this depends on the ability of a material to dissipate energy. So think about fluffy material, mineral wool, stone wool, fiberglass, this very fluffy material. They're very good at dissipating energy. And that's because of their structure. They're like fibrous material that encapsulate, or I shouldn't say encapsulate, but trap air between fibers. And as the sound is traveling through the material, it basically keeps going it's going through an unhomogeneous material. So imagine a material with fibers and air pockets between these fibers. As the sound is traveling through the material, it's going from fibers to air cavities to fibers to air cavity and so on. And every time there is a change, there is some energy of the sound that gets dissipated. It actually gets dissipated into heat. But the amount of sound that we typically are dissipating is little enough that the generation of heat is not, sensible. It wouldn't be used to heat a room. Obviously, it's too little. But that's what's happening as the sound is traveling through the fluffy porous absorber. The energy of the sound is dissipating into heat. And so the loss of transmission through an assembly is typically referred to as a sound transmission loss, or TL. It expresses the decrease in sound energy, and so in decibels, right? The decrease of the loudness of the sound as an airborne sound. So me speaking, for instance, I'm speaking, the sound is traveling through the air, traveling through the partition wall, going to the next room. The loss of decibels between the sound level that I'm emitting in the room versus the next room is what is a transmission loss, and is measured again in decibels. So how do we do these kind of things? The first obvious way to assess the performance of an assembly is to do testing. And so there is also, just like for the noise reduction coefficient, we can test assemblies using standardized test methods from ASTM. So before I go into the details of the method, I won't go too much detail, but before I speak a little bit about the detail of the test method, just want to show a very typical photo. So this is a photo from a test lab, in this specific case, a very historical one based out of Chicago, Riverbank Acoustical Lab. And you can essentially see two rooms. They are called reverberation rooms. So they are, in this case, you don't want to absorb the sound within the rooms with porous material on the walls, because you actually want to make sure there's as much room emitting in one room that transfers through the material you want to test to the next room. You don't want to dissipate sound through different areas. So this room tends to be very echoey, very high reverberation. If you speak in one of these rooms, you will basically imagine like a church or a space where there's a lot of echo. And so you can see this big opening in the middle. This is where you will insert the specimen that you want to test. So you have two rooms. On one side, you're going to have a source that will emit sound, so essentially a speaker, and the sound that's being emitted is very standardized sound. It's not any sound, obviously. And on the other side of the room, you're going to have microphones that are measuring the sound level on the other side, and the difference between the sound emitted in the first room and the sound emitted in the receiving room, as it's going through the specimen that you're testing, is essentially your transmission loss. So the method that's being used for this is ASTM E413. So it's also, again, a standardized rating, and it assesses how well a building element can reduce airborne sound transmission. So the photo I was showing is to measure the performance of a wall. Now imagine you want to do a ceiling or a roof. Essentially, you will have it will look very similar, but you will have a room with the opening that you were seeing on the photo, which is typically receiving the sample. That opening, it will be between a room that's above a second room. So this apparatus obviously also exists. This lab typically will have these two chambers, one with two rooms to test walls, and one with two rooms, one on top of the other, to test ceilings and roofs. And so in this typical test method, what we essentially measure is data that will eventually allow us to calculate STC. So the method itself that's used in the lab is ASTM E90. If you're interested to read it in more details, the standardized rating that defines STC, the sound transmission class, is E413. And again, that transmission class is essentially a single number rating that's used to simply assess the performance of an assembly. So during the E90 test method, you will basically, through the room with the speakers, emit sounds of various frequencies that you want to consider, measure how much transmission loss you have for each frequency in the receiving room, but then using ASTM E413, in order to simplify the comparison of assemblies, you run this data through some kind of calculation, which I will not go in depth in now, but you run this calculation, these measurements through some kind of calculation in order to extract what's called the sound transmission class, which is typically a two-digit number, so 36, for instance. So you can see on the chart on the right here, on the x-axis, you have the frequency. So remember, the frequency is the characterization of the sound. The lower the frequency, the lower the pitch. The higher the frequency, the higher the pitch. For typical building elements, which represent the typical noise within a home, for instance, we are considering frequencies going from 125 hertz all the way to 4,000 hertz. And so these are the black dots on the charts are the measurements that we've done in the lab. And then the red dot, the curve with the red dot, is called a contour curve. And ASTM 413 explain how to calculate that contour curve. But essentially, it's creating a more standardized curve out of a complicated measurement of transmission loss. And so from this red curve, you will read the transmission loss at 500 hertz. That's what the STC rating is. So in this case, if you look at the blue line is reading the red point at 500 hertz, and it's assessing that the STC of the specific assembly that was tested here is 36. So I realized that this may be a little bit complicated for many going in so little time if you're not already familiar with these concepts. But I think the bottom line of what I want to say here is that STC, that's the typical way we use to measure the performance of an assembly and compare one assembly with another. But what I want you to understand is that this is over a specific range of frequency. So if you're doing some very advanced acoustic, you may need to consider frequencies that have not been considered into this specific test that we typically tend to use all the time. And the second piece that I want you to take away from this is that the STC is a very simplified measurement of the performance of an assembly. So if you're dealing with specific commercial space, I don't know how many of you here in the call may be dealing with more complicated spaces, but let's say an office space next to a manufacturing space that may have, machines, rotating machines, engines with very high frequencies or very low frequency. This kind of STC assessment may not be capturing the information that you need in order to really choose the right performance, the right assembly for that specific case. So STC is a very useful information, but it's not applicable to everything. It's typically designed for interpartition of, offices, residential homes, things like this, or like, partition within a hospital, partition within a retirement home, and so on, right? But it's typically for interpartition floors and ceilings. And that is, again, because of the STC, the frequency range, the range of sound frequency that it considers. So different photos, you remember earlier I was showing a photo with the two spaces and the gap, the hole in between. In this specific case, you can see the wall has been built. The specimen that's going to be tested has been built. So when you do this testing, you typically don't finish with your gypsum board with mud and paint and so on, because it's not really necessary and because it will take time, cost money, etc. So typically you use like a non-absorbing tape, so you can see the aluminum tape over the fasteners and the joints of the gypsum board on the left side. On the right side, you can see that the wall that's being tested, there is a different kind of putty that's being used to seal these little holes that will normally be covered with plaster and paint. But essentially, what you're seeing here is an interior partition being tested. So imagine here you see the interior one side gypsum board. Behind that gypsum board, you will have batt insulation and studs, and then on the other side, you will have maybe another gypsum board or something. Now, I was saying STC considers a certain range of frequency, which are really representative of the type of sound that we will be dealing with in an office environment, a home environment. But obviously, the acoustic between the interior and the exterior side of a building is also very important. Imagine, a very well-designed passive house home, but that end up being on the path of an airport, for instance. And obviously, then the noise of the airplane is going to be radically different from a frequency standpoint, the loudness, as a matter of fact, and the frequencies of the engines of an airplane are quite different from the frequencies of a person speaking in an adjacent room. And so there is a different rating, which is the OITC, outdoor indoor transmission class, that exists, which is more specific to outdoor noise, and it considers lower frequencies that are representative of road noise, train track noise, these kind of things. And so typically you would want to use OITC for the exterior enclosure of the building. STC is for the assemblies within the building. OITC is for the enclosure of the building. And so it uses the same ASTM test method, so same room, same apparatus, defined by ASTM E90, but it uses a different way of calculating, and it covers a wider range of frequencies to come up with the OITC. So eventually, what you end up with is same test, just a wider range of frequencies, but same test. But so what you end up with is just a different calculation that better represent lower frequencies. You can notice here on the frequency range I provided, instead of being 150 to 4,000, it's 80 to 4,000. It's considering the lower frequencies, but it's also in the calculation itself putting more emphasis on these lower frequencies. One thing that's important to note in acoustic is low frequency sounds carries a lot of energy, have long wavelengths. They are much harder to block. It's quite easy to block the sound from a baby crying with a fairly typical assembly because it's a high frequency. Low frequency sounds with long wavelengths, imagine it's the same as waves. Think about the waves of the ocean. Big waves are much harder to block than waves with small little waves with low frequencies, right? So the wavelengths is very important. And typical building assemblies to long wavelengths, low frequency sound look very thin. They don't do a whole lot. So in other words, if you want to deal with very serious airplane noises, you're better off building a thick concrete wall than a steel stud assembly with half-inch gypsum on both sides. So important to keep that in mind. If you're building a home next to train tracks, the performance of the exterior wall is going to need to be much higher to create the same level of comfort within the home than if you're building a home next to a school, for instance, in a neighborhood next to a school, because again, the frequency of the sound is so radically different. So these tests are very good. These standardized ratings are very useful. It is important to understand they have limitation. I've already talked to the fact that they simplify a lot the assessment because they transform the performance of an assembly over a wide range of frequencies into a single, number. And they don't consider impact noise. So a high STC floor doesn't mean that someone with high heels or a kid running on the floor, the space above will be blocked, because these are structural borne noise. They are impact noise that are transmitting through the structure. And they also do not consider flanking transmission. So remember, if you built a very good partition between two meeting rooms in an hospital, but you don't bring the partition all the way to the roof or to the structure, the deck of your floor, you will have flanking paths where sound can travel. And I love the example of an hospital because imagine of the office space between, like with doctors having conversation with patients. In that case, there is a privacy ID that's so important, right? It's very important for us to design this room with a good acoustic level, so the conversation that is happening in one room does not easily transmit to the next room. So it's very important to consider, again, this flanking path. A much more maybe obvious example in a residential home, you built a very good partition wall, and then you put outlets back to back, you don't air seal them well, and you end up with having a flanking pass through these outlets in the wall. Even though you had a great wall, you ended up creating a hole in your acoustic barrier. So there's lots of different flanking pass types that have to be considered. Again, residential side of things, it's probably more obvious to think about vents, about outlets, things like this. In commercial space, the very typical one is a partition wall that doesn't extend all the way to the top of the ceiling or floor structure. So there is a rating for this that consider flanking transmission. It's called ASTC. It is much more complicated and require much more advanced testing because it considers transmission through, the connections between floor and ceilings and so on. But there is data there. There's a lot less data. And even from Rockwool standpoint, for instance, it is true to say we have much more information about OITC and STC, much more testing available than testing with the STC, but there's ways to assess flanking pass anyway. And again, importance of air sealing. I love talking to a passive house crowd because I know you guys are very serious about air sealing, but for once, we're not just talking about air sealing of the exterior envelope, we're also talking about the air sealing of partitions, for instance, if you're dealing with the acoustic performance of an interior partition. Air sealing is not just about the energy and the enclosure, obviously. So in the code, there's lots of things about acoustic, as a matter of fact, even though they are not very stringent. But in the International Building Code, for instance, Chapter 12 has specific requirements around typically STC ratings. In the California Green Building Standard Code, for instance, there is also some consideration. In LEED v4 had a prescriptive STC requirement. LEED v5 has moved to a different way of assessing, but ultimately it results in the same kind of process and thinking in the design phase. And then the well building standard, there's lots of different acoustic requirements out there, but they're often not very stringent. They're often overlooked. And also there's other guidelines, but they're often not used at all. But it's interesting to just note that if you are looking for guidance to focus better on acoustic, there is a lot of information available out there. And it's good to get an idea of what is a good level. We've talked about STC, and earlier I showed an example for an STC 35, if I remember. But the big question is an STC 35 good? Well, just to not keep too much suspense, I will say no, it's not very good. STC 35 is quite low, but all these codes and guidelines will help you getting familiar with the range of performance that are required based on different scenarios. And so, as a rule of thumb, I will say below STC 50-55, you're not really doing much. You're basically just doing what you've been doing forever from an acoustic standpoint. If you want to start getting into better acoustic levels, 55, I would say, is a good number to have in mind. 55 and above, you're starting doing good acoustic design, even though, again, I'm simplifying a lot, right? We talk about the frequencies and sounds are different and so on. But 55 is a good number to have in mind. 50 is quite okay. 55, you're starting to do something good. You're starting to provide better acoustic. So how do you improve the acoustic performance of assemblies? There's essentially three big things you want to do. The first one, add mass. I said it earlier, sound is a vibration. The heavier an assembly, the more energy it requires to start vibrating and transmitting sound, the better it's going to be dissipating the sound. So add mass, either by, of course, we don't necessarily want to build everything out of concrete. And, like everything else, it's always, a compromise between thermal, embodied carbon, acoustic, and all of this. But to add mass, an example is to go from 1/2-inch gypsum board to 5/8, from one layer of 5/8 to 2 layers of 5/8, etc. But this is how we can add mass. Decouple. The coupling of the size of an assembly will make the sound transmission to that assembly easier. So what can you do to decouple? The easiest way is to use things such as resilient channel. I don't know if you're familiar with this. They're like a specific kind of little Z profile that will be attached to your studs and on which you will attach your gypsum board on your drywall. And they typically get installed horizontally. And what they do is they reduce the rigidity between the gypsum and the framing, making it more difficult for the sound to travel through the assembly. Resilient channels are quite cheap, very easy to install, and extremely high performance. And then you can do more complicated things such as using double stud walls, things like this. If you're dealing with steel studs, obviously the thinner the gauge, the better it is. The idea is to reduce the connections between the one side of the assembly and the other. And finally, you want to add absorptive material and damping. So if you have an empty stud cavity, fill it with that. That's probably the most obvious example. Now, it's important to think that all of this needs to be done kind of together. You cannot really just do one and expect the assembly to be great. They're all very essential because they do different things. And so whenever you want to design for better acoustic, you want to think about these different parameters. So let's just give an example. And I realize I'm close to the end here. So I definitely need to conclude soon. But so on the left side, you have a typical assembly. So in this case, I chose steel stud assemblies. I'm sure in the call, there's many people that maybe do more wood studs if it's residential, but the logic remained the same. So here you have a basic assembly with 5/8 gypsum board on both sides and 25 gauge steel stud at 24 inches on center, filled with bats. a very typical assembly in a commercial, partition wall in a commercial building. So you get an STC 45 to 49 because you have the cavity filled with absorptive material and you have 5/8 gypsum. Notice the performance is not that bad. Even though if you remember, I said below 50, you're really not doing anything that great. You add gypsum layers on both sides, you can expect to go all the way to 54. Remember the STC scale, it's a decibel scale, it's a logarithmic scale. The few STC points means a massive improvement of acoustic. 3 points, decibel points, is essentially equivalent to a reduction of half of the energy transmitted. So it's a very, very significant improvement to increase your performance of your assembly by a few points. It's not like an R value where an extra R1 is not much, an extra STC point is a lot. And then so in the second example, we had reduced the gypsum thickness to 1/2 inch, but we had double layers. In the third one, we do double layers on each side of 5/8. Then on the one with 55 to 59, we have added resilient channels. So see how just one extra layer of gypsum and a resilient channel is technically taking your STC from 49 to maybe 59. It's a tremendous improvement. It's an absolutely major difference that everybody will actually absolutely feel. And then in the last one, we're showing an example with, staggered studs. And obviously this is increasing significantly the thickness of the wall. So it's typically not my preference to do this because space is important. But so it's just to illustrate the different things you can do. Note also in the last example on the right, we're using specific gypsum boards, which they're like acoustic gypsum board with specific layers inside the gypsum, which significantly increase the acoustic performance. So there's a lot of different tools you have available to increase the performance of assemblies. With a ceiling, same thing, a basic ceiling with no batt, a plywood floor or an OSB subfloor, some joists 2x10, and then a gypsum board, STC 23. It is miserable. You will absolutely everything through an STC 23 floor. You'll be hearing the dishwasher. You'll be hearing the furnace in the floor below. You'll be hearing absolutely the conversation. 23 STC is miserable. Note that you just add a little bit of batt insulation, and you're already bringing that STC 31. 31 is still miserable, but it's already much better. Not by adding just a resilient channel and the batt, you've brought your assembly to 45 to 49. It's an incredible improvement. You went from absolutely miserable to something actually quite decent, which in most typical residential setting will actually do pretty good. Also, for many of you on the call, which I'm sure design passive house buildings, it's probably interesting to note that because your enclosure is so high performance, your isolation from street noise is probably quite good. As a result of this, it can increase the feeling of discomfort from interior noise in the house because they're no longer covered by things that are happening outside. So a very good enclosure will accentuate the effect of mechanical system, of people speaking in the adjacent room and so on. So it's always interesting with acoustic that, what you're doing will impact other things. So in a passive house, typically the outdoor noise are well addressed because your house is so airtight, because you have so much insulation on the exterior side. But now the interior noise can become a bigger problem because it's no longer covered by the noise from the street. And just to really quickly finish, because I do need to conclude now, I just wanted to provide just some an illustration here of a typical low slope roof. So this is a flat roof. I don't know if many of you on the call do flat roof, but this roof was designed for it was a case study in New York, in Yonkers, New York. It was a sound stage where they do filming really close to train tracks. And they needed to have a very, very high performance building because the train tracks had like train every minute or so. And they're like filming inside the space. So they certainly couldn't hear the noise of the train going by in the recording. So this is an example of a very high performance roof where what you're seeing here is the corrugated metal deck with what's called flute fillers in the flutes, which are essentially absorptive material you put in the flutes to improve the performance of the acoustic. And then they have 3 layers of dense deck, like 3 layers of gypsum then an hybrid insulation solution with stone wool insulation over ISO, and then another 2 layers of dense deck. This assembly was close to an STC 7, but even though I recognize I had said earlier you should be talking about OITC. I don't quite remember the OITC of that roof, but the STC performance of this roof was somewhere in the close to the 70. So incredible performance, but obviously this is really, an extreme case. And lastly, just to finish, just wanted to say that acoustic testing is actually much cheaper than fire testing, but it still involves going to a lab, building an assembly. It still requires a lot of energy, and so it is possible. Unlike a fire, it is possible to do acoustic modeling. Not absolutely everything can be modeled. It's not thermal modeling. Everything can be modeled with thermal. It's whatever wall design you want to model with thermally broken clips, no problem. Everything can be modeled. On the acoustic side, a lot of modeling can be done. It's not as good as thermal, but it still can be done. So if you're working on the design of your building and you don't have, you cannot find testing out there to assess the performance of the assembly you've designed or you want to use, it's actually likely possible to model it. And modeling is obviously much more economical. So it is an option. It is a recognized method. Modeling is also follows the guidance from ASTM 413. So it is well defined, well understood, and it's very much possible. This is a screenshot of what an example of a software, the one we use at Rockwool, for instance, looks like. But yeah, very possible. So it's an option that you have. And so I just had a case study, but I'm going to skip it because of time, and I think it's okay. But I know I kind of went to the whole time. I don't know if there's, I'm sorry if people had to jump out of the call, but I'm happy to take any questions that you may have now.
Awesome. Yeah, I'm sure we all learned quite a bit. A lot of the sound stuff was really fascinating. In the chat, and of course, now someone has started a leaf blower or something outside of my place, so I'm listening to that. In the chat, Kim has put a queue, and if you are available to do so, I see that someone doesn't have a microphone access. That's totally fine. I'll ask your question, but as I call on you, if you are available and want to, please go ahead and unmute and ask your question. We're going to start off with Ryan McGowan. If you would like to ask your question, I think you might have had a couple. Feel free. And if not, I'm happy to ask for you.
Yeah, thank you so much. And Antoine, thanks for the presentation. I thought that was extremely helpful and definitely learned a lot. I think you answered one of my questions about adding mass to light gauge or wood framed walls. Something that I think multiple people were thinking about was the air sealing and the short circuiting through penetrations, both in the wall, floor, and ceiling. So are there different types of air sealing? And then along with that, in a past compartmentalization test, I know that they do it's like air transmission or air tightness between the units. Does that also include testing for sound transmission between units?
Yeah, basically air testing, air leakage testing you will do for thermal will directly translate for acoustic because it's exactly the same thing you're trying to do. So in acoustic, typically, if you're dealing with a penetration through a partition wall, you're not going to use, flashing tape and membranes. You're typically going to use acoustic sealants to seal your penetration, or some kind of gasket with outlets and things like this. But the air leakage testing that you will do for the enclosure is the exact same test that you will do from a thermal standpoint. For partition wall, obviously, it's much more complicated. You wouldn't really do air leakage testing, I don't think. Unless someone has a different experience in the call, I would love to hear about that. But I don't think you will do air leakage testing you could, but it just wouldn't really make sense. But so when you're building your assembly, what it means is you will really focus on the detailing, and you will use acoustic sealant to really seal everything. Does that answer your question, Ryan? Or
yeah, just a really quick follow-up. For ease of construction and also efficiency, is air leakage like sealant better than gasketing? Gasketing seems like it would have to be specific to the component. So if you had different sizes of outlets or
Yeah,
sprinklers or
exactly.
other,
Yeah.
so would you prefer like liquid air sealing?
No, I think you've nailed it exactly. It really depends what you're trying to air seal, right? If it's the bottom of your gypsum board, you're going to use sealant, but if you're dealing with an outlet, you're likely going to be using gasket and specific, outlets, yeah, or electrical box, I should say. Yeah.
Great, thank you so much.
Okie dokie. The next question, I'm going to read for Andrew Glass. Do you have a document that has OITC ratings for some standard exterior wall assemblies?
So Rockwool does, and I think many other manufacturers do. Interestingly enough, the resources are usually. I will say I will start with Rockwool and then provide additional ideas for resources. So Rockwool does. We have like acoustic catalogs in which, based on the type of assemblies and basically these are catalogs of assemblies that have been tested, and based on the type of assembly, we'll provide the OITC, the STC, or both. So this is, and basically goes through different type of assemblies from, interior partition wall with steel stud, interior partition wall with wood studs, exterior walls with wood studs, exterior wall with concrete blocks, exterior walls with steel studs, and then low slope roofing. So that's the first thing. So Rockwool has two catalogs, one for roofing and one for walls. Then other resources typically come from gypsum board manufacturers. So, all of the big names of gypsum board manufacturers tend to have like acoustic catalogs as well. And often this acoustic catalog will pair acoustic and fire performance, which is quite interesting and useful. And there is also the Gypsum Association that has a manual with hundreds of assemblies that have STC or OITC ratings. And finally, for the people in Canada, the National Building Code of Canada actually also has a library in the code of assemblies with STC or OITC ratings. So the code is a good resource. And then to summarize, gypsum board manufacturers, the Gypsum Association, and then Rockwool has two different catalogs available on our website. And then lastly, on the Rockwool side, the modeling I was talking about, that's actually a free service that we offer. So when someone is working on a project, we can run a specific analysis. If it's an assembly for which we don't have data, we cannot model. We even sometimes actually do testing as a complementary service. Sometimes, depending on the size of the project, we even do some complementary testing, if that makes sense. So this, I would say, are probably the most obvious resources.
Okay, awesome. And Andrew Glass, if you're
I did post in the chat our acoustic wall assemblies catalog.
amazing. Okay, great. And then of course, as you guys have your contact information up, if folks want to follow up with some of these resources, this is a great way to do so. Okay, the next question I'm going to read for Mr. Andrew Fowler. As the owner and builder of multifamily buildings, what do I have the design team write in the specs in order to decrease inter-room noise complaints? Usually it's just an STC rating for a wall, but it's usually not, but it usually is not tested in STU after install, or situ after install. Do I need to include an acoustic engineer sample of certain spaces?
Yeah, so I think the STC rating is definitely a great start to include that in the spec. For floors, it's also a good idea to include the IIC rating, which is a measurement of the impact noise, because obviously in multifamily buildings, a big issue is impact noise from the unit above to the unit below. So IIC, a rating I didn't speak about in this presentation, but another standardized rating. And then, yes, it's possible for sure to require actual acoustic like control afterwards. So the measurement you will be doing on site is not going to be, and there is an ASTM standard for this. I don't remember the number, but there's an ASTM test method that explains how to do that measurement and what it should mean. Because the problem with controlling an STC is what you measure on site is not going to be the STC measured in the lab. And there's two, at least there's many reasons for that, but two very obvious ones are The real assembly you're going to be measuring on site, you're not going to be isolating the one wall. You're going to be measuring what's going on between the two space, including all the flanking paths and so on. There's going to be materials around absorbing sound and so on. So that's number one. It's not a direct one-to-one comparison. The second one is when you're measuring on site, you cannot isolate street noises and so on. Whereas test labs, they have chambers that are very well isolated from the surrounding environment. So on site, you will not be controlling the STC, you will be measuring something else. But control on site can certainly be done, and there is an STM standard that can be referenced for that.
Okay, awesome. And it looks like some folks are maybe chiming in the chat as well, so that's a great place to double check as well. Okay, then. Oh, yes, please.
Just real quickly, another big piece of that is on-site quality control, because if we're taking efforts like using resilient channel, and then folks are double piercing the resilient channel and the structure behind it, it pretty much negates the use of the channel. So there, and things like continuity around outlets and all that good stuff makes a big difference.
Yeah, you're absolutely right, Rob. And I'll say one that's very common with resilient channel, for instance, where you will have a massive difference between theory and actual performance, is that many installers don't realize resilient channel actually have a direction. Because they look so simple, they just essentially look like some small ziggurats, and they just get installed in whatever ways, and they actually do have a direction, and the direction does matter. So that's obviously quality control on site is obviously very important. The application of the acoustic sealant, all of this is just a visual inspection is already a very good place to start. Yes.
Yeah, that's definitely a good point. Okay, the next question is coming from Dermont Hannafin. Would you like to unmute and ask your question? Otherwise, I'm happy to do so. Give you just a little time. He may or may not have left the meeting. Okie dokie. I'm going to read it for him. And also, Tyler, I see your comment. Okay, the question is, does the position of the RC1 impact the result?
So yes, that's literally what I just said. I guess the position, I was talking about the orientation of the resilient channel. So RC1 is the resilient channel. The orientation of the resilient channel is important. The spacing, not as much. Typically, you will install them at 24 inches on center horizontally. I will say typically it doesn't matter that much, no. But manufacturers, they will typically recommend, where to position them on the wall. You wouldn't put one right at the bottom, but it's not a major impact, I would say. But horizontal, 24 inches on center in the correct orientation, that's a good practice.
Okay, great. And then just to follow up on that, the question is a little more so on the position within the assembly, it looks like.
The position of the resilient channels within the assembly. So, well, it depends. I will say in most cases, it doesn't really matter, because what it's doing is decoupling the one side of the assembly with the other. So the sound doesn't transmit as easily. Now, if you have a side of an assembly where you expect to have the source of the sound coming most of the time, it makes sense to block it as close to the source as possible. So you would probably want to put the resilient channel on that side, just to block the sound as early as possible to reduce the risk of the sound going through flanking path. Because imagine that if you're putting the resilient channel on the receiving side, by the time the sound gets to the resilient channel, it's already gone through the structure of the wall, and therefore the studs they are connected to bottom plates and top plates. Bottom and top plates are connected to subfloor and ceiling above. So you want to block as close to the sound source. So in most cases, sound can come from either way, right? If it's two different meeting rooms, there's not one meeting room that's always going to be louder than the other. But if it's between a bedroom and a living room, for instance, maybe you could have to make the assumption that the living room is more often going to have the source of sound, and the person in the living room, in the bedroom, is likely trying to sleep. So, but I say it's a case by case. If it's obvious, yes, put it on the source, on the side of the source. Most time it's not obvious.
Okay. I have a follow-up to the follow-up, and then we can go to J.R. Frank with the next question. But the follow-up is thinking about a demising wall in a multifamily building. Your detail showed the RC1 on top of 2 layers of drywall on one side of the wall. Can it go on the other side with just 1 layer?
So with area separation wall, it's a bit of a more complex scenario because you essentially have to meet a specific fire rating, a 1 hour, 2 hour fire rating. So the easy answer to this question is do whatever the listing allows you to do. That's probably the safe answer. Now, it's a very interesting topic, and I'll actually say we are currently us Rockwool conducting testing on demising wall because the acoustic performance of this wall is often neglected, not by the builders by any means, but by the listings. The people who have developed the listings are worried about meeting the fire rating with with the cheapest assembly possible, which is very understandable. But shaft liners and things like this, which are often used in area separation walls, they typically don't do a great job at acoustic. And obviously, these walls are very important from an acoustic standpoint. And so there is a bit of a lack of understanding on how to do this properly, which is why we are currently conducting testing on this specific topic, trying to develop solutions that are optimized from an installation standpoint and material standpoint, while delivering STCs of at least 55. There are some listings out there that will actually include resident channels as an option in order to make the acoustic performance of the demising wall better. So what I will suggest is really to look what the listing allow. If it doesn't talk about acoustic and it's known that this specific solution is not good for acoustic, then I would recommend to look for a different solution. I'm not sure who asked the question in the call, but this is definitely a conversation if there is interest that I'm happy to take offline and discuss, either me or someone in my team to discuss solution because we're very familiar with that topic. And these type of walls are very, very, very often major issues when it comes from acoustic because the focus has only been on the fire performance.
Great. Awesome. Thank you. Yeah, Robert, I see you opening your mouth.
Yeah, Antoine, there was one question which I was going to answer online, but I thought we might get to, and it was about increasing the depth of insulation in a floor slab or in a floor plate, I should say. And my knee-jerk reaction was going to say that more than 6 inches of bad insulation really doesn't get a huge ROI, but
yeah,
a lot of the things that we
true.
talked about, I think, are the ROI in those situations, especially like footfall.
Yeah, so basically what each component is going to do is going to be dependent of the rest of the assembly. You cannot really provide a general answer and expect that to be true. There's no such thing. Acoustic is really, it's like thermal. The details, the clips, the rail, the framing, the subfloor, the thickness of all of this has an impact. And one material alone doesn't tell the full story. So, in many typical, very basic floor assemblies, well, let's say if 2x10, lumbers, and then some kind of OSB subfloor and a drywall underneath, I will argue that 6-inch even already is maybe too much. The difference between 3 inches to 6 inches may already be kind of not that big. And if you were to look at increasing the performance of the assembly with this very basic type of floors, you probably will be better off using resident channels instead of increasing the assembly, the thickness of the insulation. At least that's not the first thing you should be doing from a performance standpoint. It's great from a Rockwool standpoint, probably not the most, not the best to do from a performance standpoint. So it's important to not just answer generically because there's too many different scenarios there. I just dimensional lumbers, what kind of subfloor, what the thickness, what the floor finish, what the interior, the bottom. So I recommend to, again, whether it's me or someone else, I recommend for people who are looking into that kind of information to actually engage with, with the manufacturers, with an acoustician to understand the specificities of their case. So again, Rockwool, we offer this kind of complementary service as a technical support to our to designers and builders with trying to understand what does what in their specific scenario. But it is for sure putting more bat insulation is not the solution. There's different things, right? Sound blockage, absorption, and decoupling. These things all needs to be considered. So you cannot do a terrible assembly and just stuff it with bat. You'll be disappointed.
Awesome.
Right.
Okay.
Ryan put a great comment in there to that effect.
Yeah, so I would be cautious about this. I see the comment that floor assemblies are much more susceptible to impact noise than airborne. So I'm not sure I will say they're more susceptible. What I will say is that impact noise, airborne sound is badly addressed. Impact noise is even more badly addressed. And it's not easy to address. Putting more bat in the floor is not really going to help much with impact, for instance. And so I think it's not necessarily that they're more susceptible, is that they're just even worse from that standpoint. So we notice it even more. It's an even bigger problem. And so to reduce impact noise, what you really want to do typically is under your floor finish to include some kind of resilient layers. And floor, there's a lot of material options over there. Rockwool has an option, but there's other companies that offer very specific type of materials to install under the floor finish and over the subfloor in order to help with impact noise. So in impact noise, you remember earlier I said the position of the resilient channel as close to the source as possible, even more true with impact noise. Impact noise, you need to be as close to the source. So you want to address it right under the floor finish. You're not going to address impact noise with resilient channel under, all the way at the bottom of the assembly. So, good comment. My only thing is, I don't think they're more susceptible. I think it's just even more badly addressed, if I may say so.
I'm really curious on the Rockwool product that you use. Is it like rubber sort of feet, or is it like a gypsum product? Like what is the Rockwool product that you use?
So yeah, so at Rockwool we like to drink the stone wool fiber Kool-Aid. So everything we make is stone wool fibers. So the material we use for this kind of acoustic is actually a thin layer of stone wool insulation. So if I don't know how familiar you are with Rockwool products, but we have a rigid board typically used as exterior insulation for homes called Comfort Board 80. We'll essentially recommend to use that. Now, depending on the floor finish, you have to be cautious. You need to make sure that whatever you do above, the compressive resistance of the insulation is going to be high enough. And you want to make sure from a structural standpoint that it's going to do the job. So that's same thing if you're interested. Anybody who is interested in that kind of conversation, happy to help. But because it can get more complicated depending on the live load and the type of floor finish. But from a Rockwool standpoint, yeah, we will recommend a 1-inch layer of Comfort Board 80 typically. So same material, just more rigid than the typical bat that you may be familiar with.
We do have, I think, queued up in the deck, a kind of basic run through of all of our product offerings that we can kind of talk about real quickly as we get through the end of it. I think it's also important to mention that Antoine's team offers not just acoustic consultancy, but also a full suite of technical services around 2D and 3D thermal modeling, basic dew point analysis, Wolfie analysis, hydrothermal analysis, and all really is a value add to helping the folks that we're working with, helping support their design and making sure that they're getting the best performing assembly out of, to help meet their the needs of what they're doing, whether it's passive house or other requirements.
Yeah, and I think the crowd here on this call will understand very well because of you wouldn't be here otherwise. But acoustic, just like the rest, can only be good as a holistic approach. You just like thermal shouldn't be it's not just done through adding more insulation. It requires air tightness. It requires all kind of things. It's the same with acoustic. And, someone was asking about demising wall earlier. I was saying how demising walls were traditionally developed focusing on fire because that's a requirement that needs to be met. And now we deal with, it's so common for developers to mention this issue they have with acoustic complaints with this demising wall because they've been sold for fire, they've never been sold about acoustic. So I think where it becomes interesting to engage with the design with the consultants that are qualified in the various areas or with the manufacturers is to essentially have that holistic approach. So if you're talking with my team, for instance, one thing we'll always try to do is to try to get the most value out of the installation, thinking about thermal durability and agrothermal performance, and then acoustic, and sometimes fire when it's relevant, and all these different aspects of things that when they are being thought of together can deliver a great building. But if you really just focus on one and then later on you try to onboard the other one, it becomes, as passive house designers, I'm sure many of you in the call knows that high performance, for instance, is not something you're thinking at the end when you're trying to assemble the home. You really need to address that as early as possible in the design. And so it's the same with acoustic. There's no magic things you can do. And if someone tells you, oh, you just do this and it'll be great, it's because it doesn't understand what it's talking about. And especially if someone say, just fill this cavity with batt and your acoustic performance is going to be great. It's not going to be. It may help. It will likely help, but it will not actually do it. I cannot tell you how many phone calls we get. Well, I don't want to make it sound bigger than it actually is, but we do get phone calls of customers, typically homeowners that have done some reno. Rockwool is really known for acoustic, and they'll just tap some batt in a wall and they'll call us and say, hey, it doesn't work. And, it usually takes a little bit of investigation to understand what the problem is. But so recently, for instance, it was like a finished crawl space. Like it was more of a basement, but it was never meant to really be a basement. But the space underneath the house, which was insulated with spray foam, closed cell spray foam, is not really well done with a furnace in the middle, etc. High performance, but the space of the crawl space and the space above was completely connected from a ventilation standpoint. It had vents going all the way through the floor, and so they were trying to mitigate the noise from the furnace underneath. And so they put Rockwool insulation between the joists, and they were complaining they could still hear the furnace. I was like, yeah, of course, there's holes all over the floors because it's thermally connected through vents that are literally face to face. So anyway, all this to say, the holistic approach is key. And so I definitely recommend to engage in order to account for all these different things, right? Thermal, fire, acoustic, and embodied carbon. We can add so many other aspects, durability, moisture, all of this should really be thought of as a whole, especially for you guys that are interested into the passive house thing and building better buildings. It's really important to have this holistic approach. And I'm sure you already all know that.
It is surprising how often you have to remind folks that the house works as a system altogether. Awesome. Thank you for that. That was a nice, robust conversation about all the other key elements that go into it. Robert kind of touched on the last question that we had in the chat that was just about the floor assemblies and whatnot. And I just wanted to invite J.R. Frank, if you had any follow-up question about that, or maybe didn't get an answer that you desired from that. If you'd like to ask, totally feel free. Everybody else, this is your last call.
To address the question, I do notice that Rockwool has a 3-inch sound wall product. Would that be able to be utilized in that kind of assembly rather than 3.5 inches?
Yes. So again, it's good to look at it on a specifically, and we're happy to help with that if that's of interest for you. But yes, probably. Okay. And I will say, and it's probably true for all fibrous insulation manufacturers, not just for Rockwool, but we have product that we specifically market for acoustic performance. So in our case, it's called AFB and Safe and Sound. Some of you may be familiar with these products. And then we have other products we market for thermal performance. The reason we do this is, in North America, to sell thermal insulation, you have to do all kind of things from a compliance standpoint. And especially you need to be audited, you need to be controlled by external parties and so on. So if you sell an insulation material that's only used in the interior side of your building, it does not require to have an R value. So manufacturing it with an R value costs a lot more money, if that makes sense, because you need to do all these extra steps. If you only manufacture it for acoustic, you really just need to control a lower number of parameters. And so it allows to make a more economical bet. The bottom line to this is that all Rockwool products from an acoustic standpoint will have a noise reduction coefficient. If you remember earlier the conversation, so that coefficient that assesses the absorption performance of materials, it's a coefficient. So 0 means zero absorption, 1 means complete absorption. All Rockwool products are going to be about, an NRC of 1. So we don't actually have one product that's better than another. They're all excellent for acoustic, as good as acoustic materials absorptive materials. So it can be understanding that absorption is not the only parameters, it's all these other things. But from an absorption standpoint, whichever product you're looking at in Rockwool's portfolio, they're all going to be excellent from acoustic standpoint. It's the other things, the thermal, the fire, that's the other things that vary. But the acoustic, they're all going to be very comparable. So all this to say, again, looking at your specific case, it would be good to look at the specificities of the assembly in question. But yes, you're probably right. The 3-inch material that you've seen is probably okay. And going from 3.5 inch to 3-inch, for instance, that's likely not going to make a significant difference. It probably wouldn't be perceivable.
Thank you.
Awesome. Okay, Eugene, you got this like literally right in the saved by the bell. Okay. Would you make a comment about flanking noise from furnaces being mitigated by acoustic panel lined ducting or some kind of batting or baffling is what it says. And
yeah, so basically,
so
basically you will be doing this to absorb the sound at the source, right? And so of course it's going to work. Now, how much, it depends on it depends on the specificities of the case, but using absorptive material to wrap, to isolate, and to absorb as much sound as the source as possible is a good idea.
Awesome. Okay. Okay, I think we have covered everyone's questions and some great comments that have been made in the chat as well. Kim has put some additional layers of contact information in the chat, but you all have this screen in front of you now. So, we invite you to connect with folks and ask away your questions with some emails. And thank you to the speakers for a pretty robust and awesome conversation. I learned a lot about sound. Can take them into my projects with me. So thank you so much.
Thank you, Sarah. It's always this kind of conversation at PHA. So that's why we're here for the nerdery.
Yeah, exactly. My favorite group of nerds, as I say all the time. And have a good rest of your mornings, afternoons, evenings, and wherever you are calling into, everyone.